Okay, class. We are going to be taking notes on 9.1, which is on simple harmonic motion. There are a lot of equations here, so please make sure you have your data booklet and that you're referring to it, taking notes on it, and just making sure that everything makes sense. Let's begin. Simple harmonic motion is merely the periodic motion in which the restoring force and the acceleration are both proportional and in the opposite direction of the displacement. Below are some examples. The two that we are going to be focusing on in IB is the pendulum with the bob that is going back and forth, and with the loaded spring. There is a relationship between oscillations and circular motion. So you're going to see a lot of referring back to our circular motion unit. And the really neat thing is that the motion in a circle has the same pattern of movement as simple harmonic motion. You will have seen already that we have the same terms such as frequency and period, and there is a reason why. We can actually show this relationship between circular motion and simple harmonic motion by this setup here. We have a sphere that is placed onto a turntable, and this turntable will rotate at a constant angular speed. The pendulum here is placed, it's arranged so that it is in line with the sphere, and it has the same period as that of the sphere. Remember, a period for an object that is in circular motion means that it completes one full rotation. For a period here, for the pendulum, it means the full back and forth motion. We have a light that is turned on so that the pendulum bob and the sphere can be seen on the screen behind it. And what you have when you move both of these objects going at the same period, we see the sphere moving in a circular motion, and we see the oscillatory motion of the pendulum. The result is that the motion of both are identical. They share the same periodic time. If you would like to see this demonstration done, this is the YouTube video that you can watch. It's also going to be embedded into the notes below. So feel free to take a look at that. It's a professor at a college who decided to do it. It's a little bit different, but what you will see is the light is showing on the screen behind it, and you will see the periods pretty much the same. Let's take a closer look at the relationship between a circular path of an object with that of, for example, a pendulum or the loaded spring that is a simple harmonic motion. Here we have an object that's traveling in a circular path. If the object were traveling at, let's say, 1/4 of the way around the circle, we would have the radius as the blue line, and we also know that the object has moved an angle of theta. The amount of distance that the object has subtended is s. So these are our variables that we already know and have learned from our circular motion unit. We also know that omega, which is the angular speed, equals the theta divided by t. When we move that around and solve for theta, we get theta equaling that of omega times t. Because the rate of rotation is constant, the angle theta is proportional to time. We also know that the time it takes to go around one full cycle or one full circle is known as a period, and that is equivalent to 2 pi radians or 360 degrees. We can find the x and y components along this circular path. For our y component, we have that equaling to r sine of theta, and our x component is r cosine theta. These equations represent the max values for the x and y components. They are identical to that of the radius. Using your calculations for y at time t, as the object moves around the circle, you can plot a graph of displacement versus time that would look like a sine curve. Here is an example of a sine curve of an object such as the pendulum that is undergoing a simple harmonic motion. Note that the radius is the amplitude that is in the sine curve, and that the amplitude goes from the equilibrium point to the crest or to the trough, the lowest points of the sine curve. Also, what you'll notice is that the period is equivalent to that of theta. As the object moves around in a circular path, it does so in radians. So we have t divided by 2, or we have t, 3t divided by 2, and 2t. If you look in your data booklet, you will see two equations. The first equation, x equaling x sub 0 cosine omega t, this was taken from the x component on the circular path that was shown here, where the object was going around in a circular motion, and we had our y and our x components. Notice that the x sub 0 replaces the r, and theta is replaced with omega t, and that comes from the equation theta equaling omega t, and we're just replacing it with that. If you look at the pendulum below, the same equation applies. The x sub 0 replaces the mg, which is the weight, right here. The second equation is also in your data booklet, and that is x equaling x sub 0 sine of omega t, and that is just the y component. In the equations in your data booklet, they are all showing x only as the variable. Because both the x sub 0 and y sub 0 are equal to the radius, they are the same, you can use both variables interchangeably. From our circular motion unit, we learned that omega was called angular speed. However, in simple harmonic motion, we call the omega angular frequency, and this is because there is a relation to frequency of that motion. And it is denoted as this equation down here, and it is omega equaling that of 2 pi over t, and the reason, or the way that we got that, was we used this equation here, which is omega equaling 2 pi frequency, and we know that frequency equals 1 over t, and when we plug that in, we get our equation. Just as simple harmonic motion correlates with omega, the velocity can be interpreted within a simple harmonic motion as shown in this equation. Here we have velocity equaling r times omega, and this is familiar to us. When we take into account the x component, here we have the radius being x cosine theta times omega, giving us this equation down here, which is velocity equaling omega x sub 0 cosine omega t. There is another equation that you use in order to find the velocity at a particular position. The derivation isn't necessary to know, but I just wanted to show you so that you're aware how this equation was derived. So we have been given this equation that we already derived from the last slide, and that is that velocity is equal to omega x sub 0 cosine omega t. One thing that you might notice is that there were the x and y components, and when you're looking at an x and y component from a trigonometry standpoint, we know that that is just pretty much, we have the sine, we have the cosine side, and we have a right angle. So we are pretty much just using the Pythagorean theorem, which looks like this. It would be sine squared theta plus cosine squared theta equaling b squared plus a squared over c squared, equaling 1. That's equivalent to sine squared theta plus cosine squared theta equaling 1. Using this equation here, we can substitute cosine into the velocity equation down here. So let's solve for cosine, and that would give us cosine theta equaling plus or minus the square root of 1 minus sine squared theta. Next, we're going to go ahead and substitute that into the velocity equation, and we get an answer of velocity equaling plus or minus omega x sub 0 and the square root of 1 minus sine squared theta. From our x and y components, we know that x equals x sub 0 sine theta. When we solve for sine theta, we get x divided by x sub 0. We plug that in and we get v equaling plus or minus omega x sub 0 times the square root 1 minus x divided by x sub 0 squared. Here is an example. An object oscillates simple harmonically with frequency of 60 Hz and an amplitude of 25 millimeters. Find the velocity at a displacement of 8 millimeters. Go ahead and try this and start the video back up when you're ready. Okay, so we're given 60 Hz and an amplitude of 25. We need to get to a velocity given that we know the displacement at being 8 millimeters. What we can do first is we can use this equation here in order to solve for our angular frequency. That way, when we put it into our velocity, which is here, the velocity equation, so the first thing that you want to do is solve for angular frequency. And we do that by using the equation 2 pi f for frequency, and we know that the frequency is 60 Hertz, and that gives us an angular frequency of 120 pi. We then take that answer and we plug that into our velocity equation, and we also already know that our amplitude, or our highest point, is going to be 25 millimeters, and our displacement is going to be 8 millimeters. We do need to make sure that everything agrees and that it is changed over into meters. And when you plug everything in and solve for it, you should get an answer of plus or minus 8.9 meters per second. In order to find the acceleration equation for simple harmonic motion, we need to take the circular motion equation, which is a equaling v squared divided by r, and what we already know, which is the velocity, equaling radius times omega. When we plug that in to the acceleration equation for circular motion, we get a equaling r omega squared divided by r, which then the r's cancel, and we are left with a equaling omega squared x. Because we know that acceleration goes in the opposite direction to that of the displacement, we give the value a negative sign, which is shown here. One thing to note is that x is the amplitude and replaces r in the equation from centripetal acceleration. Here is an example for you to try. A butcher throws a cut of beef on some spring scales, which oscillate about the equilibrium position with a period of t equaling 0.500 seconds. The amplitude of the vibration is a equals 2.00 centimeters, which is the path length of 4.00 centimeters. Find the maximum acceleration. We are given a period of 0.500 seconds, and we have an amplitude of 2.00 centimeters. We are going to be using this equation here, and we know that omega, angular frequency, is 2 pi f. We can figure out the frequency simply by looking at the period, and we know that frequency means how many cycles per second. Well, it takes this object, it oscillates in one full cycle every half second. So we know that in 1 second, it's twice that much. So we just plug everything in. We have 2 pi times 2 hertz, all squared, divided by the amplitude, which is 2.00 centimeters, giving us an answer of 316 centimeters per second squared for the acceleration.